Hello everyone, in this video we are going to learn electron configuration. And what exactly is that? Well, if you remember, when we write electrons and the way it's configured, it's usually written in like 1s2, and then you see some number here, and then P, D, F. So this is basically all that electron configuration is about. So now we are going to learn how to exactly write that. But before that, we need to learn these four different orbitals we know as S subshell, P subshell, D, and F. Now, what is this? Well, each of these subshell can hold a certain number of orbitals. So S can hold 1, P can hold 3, so D on the other hand can hold 5, F on the other hand can hold 7. I'm not going to draw all these orbitals. Now, what exactly are these orbitals? Well, we can think these orbitals as rooms, all right? So this is one room, and each of these rooms can have 2 people, or in chemistry, 2 electrons. Now you can quite figure out how many electrons each of these subshell can hold. So for S, we can have 2. For this, we can have 6. For D, we can have 10. There should be one more. Yep, this is 5. 5 orbitals in D subshell, 10. And for F, we have 14, okay? Now, how does it work, okay? So, every time when you have to fill up these orbitals, you have to fill it up in this way, okay? So, let's imagine, let's draw these orbitals. Let's say we are going to try P. So, now we have to fill the people, or we can say fill the electrons. First guy goes here, the second guy goes here, the third guy goes here. So if you see, I have to fill up the orbitals first, okay? So it's not like, okay, first, then this. No, it doesn't go that way. First, you have to fill up the first orbital, second, third, and then, I remember, they're always the opposite. Now, one interesting thing that I have to tell you about is what happens sometimes that, let's say this is P, right? And this is S. And here we have 2. Okay. All right, so what happens? See, we have 1, 2, 3, 4, 5. And we need one more, right? Because it becomes more stable. Now, what it happens in chemistry? In chemistry, there's always these kind of exceptions that you have to take note of. What happens is that this P orbitals and all these guys are going to say, yo, S, come over here. And that's what happens. So one of these S goes here. And then this one becomes just 1. And why does this happen? Well, because a fully filled orbital is more stable. It's more stable than not fully filled. So these p orbitals, they always want to be filled. And I will explain it to you later when we go into the electronic configuration of different elements. And that's what we have here. So we are going to fill up all these for 26 elements. But before that, we have to know Aufbau principle. Let me write it down. Aufbau principle. What the hell is this, right? Well, this is actually something that a way of kind of like knowing, okay, where do I put all these electrons? Where do I put it in S? Do I put it in D? Do I put it in F? Or whatever, like where do I put it? So that's basically this Aufbau principle. It's just going to be like a guideline where to put these electrons. So the way it works is like, first we have 1, 1s, because 1 is going to have 1s, then 2 is going to have 2, so 2s, 2p, then 3 is going to have 3, so 3s, 3p, 3d, 4 is going to have 4s, 4p, 4d, 4f, and 5 is going to have 5s, 5p, 5d, 5f, and so on. Okay? Now, the way this works is that the arrangement actually follows this arrow. So first, you have to start with 1s. Then, you have to start with 2s. Then, you have to start with, was 3s. Let me write it down again. 3s. And then, you have to draw this arrow again. So then, it's 3p, and then 3d, and then this, and so on. Okay, now it's going to be more clearer when we write the electronic configuration. So let's start with hydrogen. Well, first we have to start with here, right? So 1s1, because it has only one electron. Helium, 1s2. Lithium, well, S can have 2. I will write it down again. S can have 2, P can have 6, D can have 10 electrons maximum. Okay, so this one is filled. So 1s, and then we go to the second one. It's going to be 1s2, this one, and then 2s1. Then 1s2, 2s2. You can also check that you're writing the right one. So here is 2, here is 2, so 4 electrons. Now this is 5. 1s2, 2s2. We can't write 2s3, right? Because S can have only maximum 2. So this means it goes to the next one, which is 2p1. So let's continue. Now you know, like, it's just going to be 2p1, 2, 3, and until it becomes 6. So 2p, 2p2, 2s2, 2p3. It becomes quite tedious, right? 4, 1s2, 2s2, 2p5, 2p6. All right, we're done. Now, for the next one, we have to start with 3s. Okay, 1s2, 2s2, 2p6, then, that's right, 3s1, right? Because you see, it's 2p. After that, we go to 3s1. And we know that S can have 2 electrons, so 2p6, 3s2. Okay, we are done with S. Now we have to move to P again. Three S2, 3p. Oh, as you can imagine, this is becoming quite tedious, right? So what we can do is make things shortcut, because that's what we like, right? Because we always like to shortcut things. What we can do is actually do this. And so this one, as we know, is neon. Now we are going to use this same shortcut. So whatever until here, we just write NE. So let me rest this until 2p6. We just write NE, because then we already know the configuration. NE. Okay, now we can continue again. So NE, 3s2, 3p2. NE, also write it like this, 3s2, 3p2. This is for so this is, sorry, this is 3, yeah, and E, 3s2, 3p4, Ne 3s2 3p5. So this is Ne 3s2 3p6, because p can have maximum 6 electrons. Now we are going to do the same thing, and we are going to make another shortcut, because we love doing that. So this one is now just going to be argon. So we continue here. So now we are just going to say this is going to follow the electron configuration of Ar, and then 3p6. Okay, so where is this 3p6, 3p6? Okay, so now we are going to start with 4s again. So 3p6 is over, so now we start with 4s1. So, and as we know, S can have 2, and Ar 4s2. Okay, we are done with 4s. Now we have to move to the next one, which is 3d. So 3 can have how many, if you remember? 10 electrons. So 3d 1. Now let's continue. 21, and 4s2 3d 2. 4s2 3d 3. Now this is where, as I've mentioned, some exception is where it happens. Normally, what would you write? Well, 4s2 3d 4, right? Well, it's not that simple. The correct answer is actually Ar 4s1 and 3d 5. So it's quite important, this one. Why is this happening? Interesting. Well, if you remember, okay, let's draw some orbitals here. Let's see what's happening here, okay? So this is, yep. So this is my p orbital, okay? So what happens, right? So we know how many, if I draw this, right, this 4, right? 1, 2, 3, 4. Now the thing with orbitals is that they like to be fully filled or half filled. Now what's happening here? It's not like if we could have one more electron here, it becomes more stable, and that's what these orbitals want. They want to be more stable. So what happens is that they say to s orbital, yo, give me 1, and that's what happens. So they come here from s, and so this one becomes s1, and this one becomes 3d5. And this is the same for all these transition elements from group 5 to 10. This is where this exception happens. However, when we continue to the next one, let's see what happens. For S, well, we are going to follow this. Since this is not applicable anymore, we're just going to follow this. Okay, 3d5, 4s1. Now, okay, yeah, we can put the 4s2 here, and 3d5. Now for this, we know that the S subshell is filled. Now we can put 3d6. It's quite interesting, like how you can write, and we always have this exception. So sometimes you just write it, and then you always come these exceptions, and you have to really understand, okay, why is this happening in the first place?